So for today's lesson, we will be learning how to integrate hyperbolic as well as inverse hyperbolic functions. So what are hyperbolic functions? So these functions are somehow related to our known trigonometric functions, as you will discover later. So there is just your hyperbolic sine, hyperbolic cosine, hyperbolic tangent, and so on. And the values of these functions are related to the coordinate points on an equilateral hyperbola in a similar way that values of the trigonometric functions are related to coordinate points on a circle. So if trigonometric functions is to a circle, our hyperbolic functions is to an equilateral hyperbola. So we start with the definition of the hyperbolic sine and the hyperbolic cosine. So our hyperbolic sine, written as sine, or it's read as sinh x, will just be equal to e raised to x minus e to the negative x divided by 2. Whereas cosine, hyperbolic cosine or cos x looks very similar, but it has the plus sign, so that's e to the x plus e to the negative x divided by 2. So from these two, as they are like trigonometric functions, we can also derive the other hyperbolic functions. So tangent is just equal to sine over cosine, so the hyperbolic tangent would just be equal to sinh x over cos x. So that will give us this equation. Okay, so if you want to memorize all of this, it's not a problem, but I suggest you just memorize the equation for sinh and for cos, and the other hyperbolic functions can be derived from them using the same relations of trigonometric functions, like cotangent is equal to cosine over sine. So in this case, e to the x plus e to the negative x would be on the numerator, and e to the x minus e to the negative x, which is sinh, would just be in the denominator, and the 2 will both these two cancels out. And same goes for your hyperbolic secant and for your hyperbolic cosecant. Okay, so now we will be presenting some identities using hyperbolic functions. Please take note that they look very similar to the identities in trigonometric functions, but they are somehow different. You'll see some signs will be reversed, some operations, the plus sign would be minus, and so these are the identities. So your hyperbolic tangent, of course, is just equal to the reciprocal of your cotangent, hyperbolic cotangent. So see here, there's a difference in from the trigonometric identities. So cos squared x with minus sinh squared x will be equal to 1. So same here. So in trigonometric identities, this should be tangent squared plus 1, but in here it's 1 minus hyperbolic tangent squared x, that would be equal to hyperbolic secant squared x. So 1 minus hyperbolic cotangent squared x would be equal to negative hyperbolic cosecant cosecant squared x. Alright, so here are some other identities. So cos x plus sinh x would be equal to e to the power of x, and cos x minus sinh x would be e to the negative x. So the sinh of 2x is just equal to 2 times sinh x cos x, and cos 2x would be equal to cos squared x plus sinh squared x. So later on, we may use some of these identities in solving or integrating hyperbolic functions. So now we will present the integrals of hyperbolic functions. So maybe you will find this very similar to integrals of simple trigonometric functions, but some signs would be positive from the trigonometric functions that would be negative, such as sinh u du would give you cos u plus c. In trigonometric, that would be a negative cosine. So cos u du will give you sinh u plus c. So hyperbolic secant squared u du will give you hyperbolic tangent u plus c. So the hyperbolic cosecant squared u du would give you a negative hyperbolic cotangent u plus c. The hyperbolic secant u, hyperbolic tan u du would be negative hyperbolic secant u plus c. Hyperbolic cosecant u times hyperbolic cotangent u du would be equal to negative hyperbolic cosecant u plus c. So at this point, I think we realize that they are somehow similar to the integrals of trigonometric functions, but in this case, the last part, the last three, would have all negative results. Negative hyperbolic cotangent, negative secant hyperbolic secant, negative cosecant, and the previous one are all positive. Sine, cos, sinh, cos, and hyperbolic secant squared. Let's try to solve the integral cos x all over cos squared x minus 1 dx. So we can see any pattern right now, but we can use identities to transform this integral. So we've shown earlier that we know that there is an identity for hyperbolic functions saying that cosine hyperbolic cos squared x minus sinh squared x would be equal to 1. Alright, so this is cos squared x minus 1. So if we transpose 1 here, we will get cos squared x minus 1 would just be equal to sin squared x. So we can rewrite this equation, this problem, as the cos x over sin squared x dx. So take note that this one, the denominator, is squared, so we cannot directly use identities here, but we can further transform this by separating the fraction into cos x all over sin x, that can be later on rewritten as hyperbolic cotangent, that would be multiplied by 1 all over another sin x. So if we multiply to that, would just be equal to the original equation. So don't forget the dx. So this one can be replaced with hyperbolic cotangent of x, and this one, the reciprocal of sin x, or the same as in trigonometric functions, that would be cosecant hyperbolic cosecant x. We have dx. So now we have this to answer, and we know that this one is just equal to the negative hyperbolic cosecant. So our answer would just be negative hyperbolic cosecant x. This would be plus c. Let's answer the integral sin x cos squared x dx. So now we will be using the classic u substitution, but we need to identify which is our u. So for this one, it's better to assign u with the one with the power. Don't you agree? So as much as possible, we want to transform this into a simple power formula that we can integrate using our theorem. So for now, let's assign cos x as our u, and the derivative of u would just be derivative of u would be sinh, as they are both positive in the theorems for hyperbolic functions, but in what do you call this, trigonometric functions, it is different story. So now we identified u x, we can rewrite this equation as, so you have here, let me write that down as, okay, let me use a black one. So this would look like push x squared sinh x dx. So that pretty much looks like this is the integral of, this is u raised to squared raised to n, and this is your du. So du, this is a simple power formula, and our answer must be u raised to n plus 1 all over n plus 1 plus c. Okay, so what we have here is just plug in our values. So our answer now would be cosh x cubed all over 3 plus the constant of integration. Okay, so it's very straightforward, this one using the power formula, and of course still u substitution, and simple power formula saves the day. Let's have integral of hyperbolic cotangent squared 3x dx. So we don't know a direct integral for hyperbolic cotangent, but we can use our identities. So recalling, we have an identity which says that 1 minus hyperbolic cotangent squared x is just equal to negative cosecant hyperbolic cosecant squared x. So for this one, we can transpose negative cotangent to the other, hyperbolic cotangent squared to the other side, and we will get hyperbolic cotangent squared will just be equal to 1 plus cosecant hyperbolic squared x. Okay, so we substitute this in our original equation. So we will be evaluating 1 plus cosecant hyperbolic cosecant squared x dx. So we know that we can separate this two into individual integral. So we have the integral of dx plus the integral of cosecant hyperbolic cosecant squared x dx. So this one, the integral of cosecant squared x dx would just be equal to u du would be equal to a negative cotangent hyperbolic cotangent u plus c. So we just plug that in. Integral of dx would just be x. So our answer would be x plus c, of course, and x minus, oh sorry, I forgot, this is 3x. This is 3x. So negative hyperbolic cotangent 3x plus c. Okay, so for this integral, we first need to use u substitution, where we assign u equals 3x, and the derivative of 3x is 3 dx. So we need to see 3 dx in our equation. So if we put here 3 dx, so that we get hyperbolic cosecant squared u du, this format, we need to multiply it with 1/3. So 1/3 outside of the integral. And so our answer for this one should be, we also have here 1/3 cotangent 3x. Inverse hyperbolic functions, we have this pattern, the integral du all over the square root of u squared plus a squared is equal to arc of hyperbolic sine u over a plus c, or that in natural logarithm, that would be equal to ln u plus the square root of u squared plus a squared plus constant of integration, that is if a is greater than 0. The next one is similar to the first one, but in this one, what's inside the denominator and the radical sign is u squared minus a squared, which is equal to the arc of the inverse of the hyperbolic cosine u over a plus c, or in natural logarithm, that would be ln u plus, so it's just the same as the denominator, the square root of u squared minus a squared plus constant of integration, that is if u is greater than a and a is greater than 0. The third one is there's no radical sign in the denominator, that would be integral du all over a squared minus u squared, that would be equal to 1 over 2a ln the absolute value of a plus u all over a minus u plus constant of integration. That is if u is not equal to a and a is not equal to 0. So that is equivalent to 1 over a hyperbolic inverse of the hyperbolic tangent u over a plus c if the absolute value of u is less than a, and if the absolute value of u is greater than a, that would be equivalent to 1 over a, the inverse of hyperbolic cotangent u over a plus c. Example, let's have the integral of dx all over 25 minus x squared. So looking at this, I believe you already have an idea which of the inverse hyperbolic function integrals we can use. So let's transform this one as, so this would be the integral dx all over 25 is a perfect square, that's 5 squared minus x squared. So if we will be assigning the values here, u would be x, a would be of course 5, and the derivative of u, derivative of x would just be 1 dx. So our pattern here would look like that's du all over, that's 5 squared or a squared minus x squared, or sorry, u squared, that's u squared, and that is equal to 1 over 2a, the ln of the absolute value of a plus u all over a minus u plus our constant of integration. So since we already identified our u and our a, we will just plug it in this equation and find our answer. So our answer would most likely be 1 over 2 times a, or 2 times 5, that's 10, the ln of the absolute value of 5 plus u, sorry, 5 plus x all over 5 minus x plus the constant of integration c. So that is satisfying the condition that a is not equal to 0 and u is not equal to a, because if that's the case, this the expression in the absolute value symbol would just be equal to 0. Oh, sorry, that would be undefined. Okay, so those are your conditions. Another integral using inverse hyperbolic functions. So let's have the integral dx all over the square root of x squared minus 6x plus 13. So looking at this, we have a radical in the denominator. We are dealing with the inverse hyperbolic functions, so it can only be between the first two theorems that we presented. So let's see if we can transform the what's inside the radical in the denominator into either u squared plus e squared or u squared minus e squared. So let's look at this first and second term. So we actually have x in the first term, so we know that our expression will have x. There is a minus sign, so we also know that there will be minus between them, and this is the middle term, so we should just divide this by 2. So the number we are looking for is actually negative 3. So we want to have x minus 3 as our u, or in this inside the radical symbol it should be u squared. So if we square that, this would be equal to x squared minus 6x plus 3 squared, so that would be 9. Okay, so since we have 13 here, which is greater than 9, we can add 9 here and subtract 9, all the same, and that would give us 13 minus 9, or 4. Okay, so let me rewrite the transform equation so that we can have a better idea which values to assign. So we have dx all over, so this is supposed to be x squared minus 6x plus 9 for the perfect square, so that's x minus 3 squared, and that would be, since we add 9, we also will subtract 9 here. Let me just write that down. So we will be adding 9 and we subtract 9, so basically we just add 0, so it didn't change the equation. So 13 minus 9, that would be 4, so that would be plus 4, or let me just write that down as 2 squared. Okay, so now we can assign our values. So here, of course, our u would be x minus 3, and our a would be 2, and the derivative of x minus 3 would just be negative 3 would be 0, and x would be 1, so that would be dx. So we will be looking at the pattern of the integral. We have du, which is equal to dx du all over the square root of, we have u x minus 3 u squared plus a squared. So we have u squared plus a squared inside the radical sign in the denominator, so that would give us ln u plus the square root of the same u squared plus a squared plus c. with the condition that a is greater than 0. So a here is 2, so that's pretty much greater than 0. So now that we identify the pattern, we just need to plug in our values. So that would be ln eu, that would be, okay, let me use a bigger bracket, x minus 3 will multiplied by u squared. Let me just write u squared, or okay, let's write the original one, because we really didn't change anything. So that would be x squared minus 6x plus 9 plus 4, so that would be plus 13. And we'll close the brackets. Please be very particular here, be very careful, because when you input this in your calculator, you might get syntax error if you miss some brackets. Okay, plus constant of integration. Okay, so it's just identifying which theorem we can fit our current equation or problem, and using u substitution to the identified theorem, and basically just plug in the values. Let's answer one more. Let's answer the integral dx over the square root of x squared minus 25. So now we have a radical sign and two squares in the denominator. So let's rewrite it as dx all over x squared minus 25 is 5 squared. So from here we can identify using u substitution. It's u is none other than x. A would be the constant 5, and the derivative of our u would just be 1, or dx. So we already recognize that this pattern would be equivalent to du all over the square root of u squared minus a squared, and that is equal to ln of u plus the same thing in the denominator, u squared minus a squared plus our constant of integration. So the only thing left to do is to plug in our values. So this one will give us ln of u, which is x, plus the square root, the same thing as the denominator, that would be x squared minus 25 plus our constant of integration. So This is given that a is greater than 0, so 5 is greater than 0, and u is greater than a. So right now we don't have a value for u yet, so we can't know for sure. So we can also write it down as cosh sorry, of x over 5 plus c. And so that would be all about hyperbolic functions and inverse hyperbolic function integrals. So I hope um, you learn something and your techniques in integration has improved using the u substitution and this various theorem that was introduced. And if you have any confusion, our source book was still the Calculus 7 by Leithold, and you can read this in pages 512 to 524 of that. So thank you for your time, and good luck on your problem sets, and goodbye.